Good day, everyone. Welcome back to another great section of this wonderful tutorial class. Today, we are going to be looking at a very important topic in physics, which is current electricity. Now, what is the meaning of current, and what do we mean if we are saying quantity or current? And how do we define it, both mathematically and otherwise? Now, before we go into this topic properly, I will advise you to distance yourself from anything called distraction. Don't skip any part of this video. Ensure you watch the video from the beginning to the end. And please, if there's anything you don't get, you after you have watched the video from the beginning to the end, you can start all over again, watch it continuously. Because the more you watch, the more understanding you get. So that's how it works. So if you know you are not subscribed to the channel, please try and subscribe now, and please turn on your notification bell so that anytime we release any video, you'll be the first person to see it. So what is the meaning of current electricity? Now, current electricity is the rate at which charges flows. Is it what? The rate at which charges what? Flows, or the ratio of charge to time. So when you divide the charge flowing in the conductor by the time at which that charge is flowing, we are going to have a quantity called current. Now, current is a fundamental quantity. For current is a fundamental quantity with the unit ampere, which has a capital letter A and the symbol. And this is the symbol for the unit of current, which is ampere. Then the dimensions can either be in this A, or you can also use I as its dimension. So it's a fundamental quantity, take note of that. And mathematically, if you want to define current I will be equal to charge over time. That is charge per unit time. We can ask you, dash is the charge per unit time of a material or of a conductor. The charge per unit time of a conductor is called current. Current in that conductor. Now, we said I, which is the current, is equal to Q over T. Now, Q is charge, T is time. T is time. Then, using differential calculus to express this definition, the rate at which charges flow, that is something like change in the charge flowing over change in time. So if you move that to differential calculus, we are going to have that current will be equal to dq over dt, which is the differential coefficient of charge with respect to time. So the differential coefficient of charge with respect to time is called current as well. Take note of that. While current, if you want to look for this charge now, this charge will be equal to R times T. Give us IT. So IT is equal to charge. Take note of that. IT is equal to what? Charge. Then you can ask you, dash is the product of current and time. The product of current and time is called charge. That's what we call it, charge. So from here now, from this place, you can obtain the dimension of charge. You can obtain the dimension of charge. Let's move on first. Now, if current is not given as a function of time, now this will work out if charge is given as a function of time. So you give your charge as a function of time, you differentiate the charge related to time, and you have current. Now, if your current is given or expressed as a function of time, and you want to get the charge considered current, just integrate the current related to time, we have the charge. Simple as that. So, when you look for current, you differentiate your charge. When you look for your charge, integrate your current. This is called integration calculus. This symbol is DD. They are called differentiation calculus or differential coefficients. So, we are still going. I said we can get the dimension of charge from this place. We already know that the dimension of current is either A, or you can also use I. The unit of current is ampere, which is A. That is something like a symbol we use on to measure ampere. So the dimension of this current now, the dimension will not be, what is the dimension of the direction of charge now, what is the direction of current? It's either A or I. So we have A. Now what is the direction of time? Capital letter T. So time is also a fundamental quantity. Time is also a fundamental quantity. Take note of that. And look at it, look at it, look at it. Just all of them, they are both fundamental. So after that, we are going to have something like this. A-T. This will be the dimension of charge. Or also say the dimension of charge is, you don't have to use A as for current, you can use I. You have times T. So that I see this way, or this C that we have the case will be. The case will be. Now, for conduction in metals, when we look at the conduction in metals, when metallic conductors are conducting this current, when charges are flowing through a metallic conductor, then we can also say current, which is the Q over the T, will be equal to the same thing as NE times VA. NE times what? Times VA. Where N is equal to, take note, where N is equal to the numbers of free electrons per meter cube. Where N is the numbers of what? Electron per meter cube. The numbers of electrons per meter cube. Then E is called elementary charge. That is what this E. E is elementary charge. Remember from chapter 1, when we charge also, we said elementary charge is also what? 1.6 times 10 power what? Minus 19 coulomb. That is E there. The V is called drift velocity. That's what we call this V. V. This V is called drift velocity. Check out that. Drift what? Velocity. Drift velocity. The A is cross-sectional area. Cross-sectional area of this conductor we are trying to look at. Then the density of this current called current density. The density of this current that we call current density will be equal to J, equal to current divided by area. So the current flowing in the conductor divided by the cross-sectional area of that conductor is called the current density. That's what we call it, current density. So this J that is called current density. Is current over what? Area. Or you want to say is equal to divide everything here by area. We're going to have NE times what? V. There will not be A. So A will cancel out E. Then if I want to make this drift velocity, is that a formula? The drift velocity will be equal to I over NE from Ohm's law. To say that V is equal to IR. That was V is equal to IR. So please, this V and this V are not the same. So I'm going to have V naught. V naught. V naught. So let us follow our V naught. This one is velocity. But this one is not velocity. So say that V is equal to IR. That is the current flowing through a wire, the exploration, this potential difference, and so on. So consider that V is equal to IR. Where V is called voltage or potential difference. Where V is called, this V is equal to voltage or what? Potential difference. I is current, R is resistance. R is what? Resistance. Look at the quantity here. And we are using this, we used this before when we were doing capacitance or capacitor. Then this current, I'm just mentioning these things, current is this and that. Then what about R? R is manual, it's called resistance of the conductor. The resistance of the conductor or the resistance of the wire. So, and from here we can say the current flowing through the wire is equal to R, is equal to V over what? R. So the current will be equal to V divided by what? R. That will be the current. And we also say the resistance of the material is equal to the voltage or the potential difference divided by what? The current. Just from this place. Want to make I or want to make I is not formula, divide both sides by R. Divide side by R will cancel R, only R will be left. Divide side by R, you have V over R. Then want to make R the subject of the formula, divide side by I, divide side by I will cancel out I, you have V over R. No, have it there. Now what's the meaning of resistance? The resistance of a wire, the resistance of the conductor is the opposition to the flow of current. The opposition to the flow of what? Of current. The resistance of what? The wire is the resistance is the opposition to what? The flow of current. So that thing that is trying to oppose the flow of current in a conductor is called the resistance of that conductor. Now there are still loads I will still call is trying to resist the current. Something like that. Some loads are still, we still call them resistance. You say, what is the resistance of this load? What is the resistance of this material? What is the resistance of this? What is the resistance of that? What is the resistance of so and so on? That is, how much can it oppose the flow of this current? So, and the resistance of a material, and the resistance of a material, the resistance of any material, is directly proportional to the length of the material and inversely proportional to the cross-sectional area of that material. The resistance of the material is directly proportional to the length of the material and inversely proportional to the cross-sectional area of that material. So if we decide to remove that sign of proportionality, we are going to insert a constant that we call rho. That's what I'm going to call it rho. We'll call it rho L over what? Over A. Where that rho, this rho is called resistivity of the material. That's what we call it. It's called what? Resistivity of what? Of the material. Then R is resistance, A is cross-sectional area, then L is the length of the material. So the resistance of the material is always directly proportional to the length and inversely proportional to what? Cross-sectional area. So from here now, what will be this rho? The resistivity of the material can also be RA times over what? Over L. This times this divided by L. That will also be the resistivity of the material. And the unit of resistivity is ohms meter. Take note. The unit of resistivity is ohms meter. The unit of resistance is ohms. That's the unit of resistance, ohms. The unit of resistance is ohms. Take note that one is still very, very, very important. Extremely important. Extremely important. So take note, we have resistance, we have resistivity. We have resistance, we have resistivity. Now, furthermore, the conductance of the material. There's what we call conductance, what we call resistance, what we call conductivity, also what we call resistivity. Take note, four of them. The conductance, resistance, conductivity, and what? Resistivity. Take note of that. Very, very, very important. Now, the conductance of a material, I will denote it by the letter G. The conductance of a material, let me call it G, is always the inverse of that material's resistance. So conductance is always inverse of resistance. Inverse of resistance. So it's going to be per ohms. While conductivity, I will use delta to represent that. While conductivity is inverse of resistivity. While conductivity is the inverse of what? Resistivity. That means that if conductivity is increasing, resistivity will be decreasing. And if conductance decreases, then resistance will increase. That's the meaning. They are inversely proportional to each other. So they are inverse of each other. Let's see good. But we know that work or energy, work is the product of what? Force and distance moving in the direction of the force, while energy is the ability to do work. I don't know if you remember the ability to what? To do work. And from the Joule's, there's what called Joule's law of heating in electricity. Joule's law of heating. Now, and from the Joule's law of heating, it was said that heat energy H is always equal to I square ROT. So said that heat energy H is always equal to what? I square ROT. I square ROT. And from Ohm's law, we know that V is equal to IR. So we can say it is equal to I times I, times ROT. We know that V is equal to IR. So this one will become RVT. So You can get this as also the formula for heat energy. Formula for what? Heat energy. Why power is the rate at which work is done, or energy divided by time. That is power. Power is the rate at which your energy is being applied, or energy over what? Over time. That is power. So that will give us energy. What is energy we have there? We have IVT. We have IVT over time. That is power. This will cancel this. So power will become equal to IV. So electric power is equal to IV, which is current times what? Voltage or potential difference. Potential what? Difference. Potential difference. And we can also say power is equal to what? We have I squared. I squared. This T, we cancel this T. Or we can also say heat energy is equal to IV is equal to power. So P times T, power times time, also give us heat energy. We can give a lot of equations and formulas related to this. We have a lot of them. So what do we do? All the formulas are given and the formula is this, everything. Please take note of them. Very, very important. Everything. Very, very important. Very important. Take notes. Very important. Very important. Why the EMF of the cell? Let's just introduce this one, although we have not entered these 6 cycles. Why the EMF of the cell? We call it EMF of a cell, which is the electromotive force of that cell. Which is the electromotive force of that cell is equal to R bracket R plus R. Where this small letter R is called the internal resistance of the cell. The internal resistance of the cell. While the capital arrow is external resistance, or the load the cell it was being connected to, or is being connected to. If you connect the cell to a load, that load you are connecting the cell to, the resistance of that load is this arrow. Then the internal resistance of the cell, the resistance of the cell is this letter arrow. The I is the current produced by that cell. The EMF now become the electromotive force of that cell. Please take note of that. Take note of that. Examples. What examples? An old electrical gadget. Let's start from here. An old electrical gadget draws 14 ampere. From an overhead line. Draws what? 14 ampere. From where? From an overhead line. At 480 volts. At 480 volts. Full stop. At 480 volts. Full stop. What power does it draw? What power does it what? Draw. You say power is equal to what? I times what? V. So this will give us, what is I? If I is I, our I is 1 ampere. I is 14. Times, what is V? 1 is voltage, potential difference, 480. So if you do this, you are going to have, we're having 6720 watts. That's 6,720 watts. That's what you're doing now. More examples. Now, let's start this. Calculate the current developed or flowing through a wire. Calculate the current flowing through a wire at 500 volts. At 500 volts. If the resistance of the wire is 10 ohms. If the resistance of the wire is 10 ohms, what is the current flowing through this wire? So, solution. Remember I tell you guys that V is always equal to what? IR from Ohm's law. Then from here we now say I is equal to what? V over R. Then what is V? 500 volts. Then what is the R? 10. So this cancel this. So we have 50 ampere. That is the current flowing through that wire. As simple as that. Very simple thing. Now let's try this. How much potential difference is needed? How much potential difference How much potential difference is needed? How much potential difference is needed to pass a current of 20 ampere? To pass a current of 20 ampere through a resistor, of 5 ohms. How much potential difference is needed to pass a current of 20 ampere through a resistor of 5 ohms? Potential difference V is equal to what? IR. Very simple thing. Then you now say okay, V will now be equal to our I is what? 20 times the arrow is what? 5. So that gives us say 100 volts. So we need a potential difference of 100 volts to do that job. To do that what? To do that job. Then next question. This is another question. A current of 1.0 ampere. A current of 1.0 ampere. That is the current. A current of 1.0 ampere is maintained in a 150 ohms resistor. It's maintained in a 150 ohms resistor for 20 hours. For 20 hours. For 20 hours. How much heat is developed? How much heat is developed in this resistor? How much heat is what? Developed. Solution. So heat energy is equal to what? So we have I, arrow, and T. So we're going to have I squared, arrow, T. We're going to have 1 squared times 15 times, look at this T. That is in hours. We want to move it to seconds. We want to move from hours to seconds. Look at what you do. We want to move from hours to seconds. Use the value to multiply 60 twice. You want to multiply 60 times 60. So this time now be in seconds. That will be in seconds. So I'm going to use that 20 times 60 times what? 60. So this is going to give us 108,000,000. That is the heat energy developed. So joules. Remember the unit of energy is what? It's joules. So this can also be as 1, 2, 3, 4, 5, 6. 6. And you can also take 10.8 times 10 to the power 6 times 10 to the power 6 joules, which will becomes 10.8 megajoules, because 10 to the power 6 is mega in physics, megajoules. Or you can just move the point from here 1, 2, 3, 4, 5, 6, 7 standard form. It will be 1.08 times 10 to the power 7 joules. It can also be the answer. This also can also be the answer. As simple as that. Very, very simple. Very, very simple thing. Now, one more question before we go. We have a lot of questions. Okay, let me just solve one more. Let's solve two. Let us solve two more questions. A wire carries a current. A wire carries a current of 10 ampere. A wire carries a current of 10 ampere at 200 volts. At 200 volts. At 200 volts. Calculate the resistance and conductance of this wire. Calculate the resistance and conductance of this wire. What will be the resistance and what will be the conductance? We have that V is equal to what? IR. We will say R is equal to what? That is resistance. R will be what? V over I. That will be equal to V is 20. That's 200, sorry, over 10. So that's this. The R will be equal to 20 ohms. That is the resistance. Now what about the conductance of the wire? What will be the conductance of the wire? What will be the conductance of the wire? So the conductance G, which is inverse of resistance, will be 1 over 20. That's 1 over 20. So this is going to give us 0.05 per ohms. Per ohms, because it's 1 over ohms. Yes, it's 1 over ohms. Then lastly, last question for today. A wire of length 3 meters. Carries a current of 2 ampere at 5 volts. The wire of length 2 meters carries a current of 2 ampere at 5 volts. Having a cross-sectional area of 4 meters square. Calculate the resistivity of this wire. Calculate the resistivity of this material. We know that resistivity is equal to what? Rho times A over what? Over L. Also remember that. And what is Rho? Rho is equals to, let me quickly calculate Rho. Rho is equals to V over I. That is 5 over 2. That will be 2.5 ohms. That is Rho. Then from here, we'll be having something very nice. We're going to have our root to be equal to 2.5 times our area is 4, right by the length is what? 3. So what are we going to have here? To solve this very well, you are going to have 3.33 ohms meters. That's what we're going to have. So please study this topic over and over again. We still have a lot of questions to look at in our next sections. So first of all, study this is section 1, the class. See you guys in our next class. I love you all. God bless you. Thank you.